So in this instance, we're going to show that the inverse Gaussian, otherwise known as the inverse normal distribution, is a member of the natural exponential family of distributions. So we begin with the form of the inverse Gaussian, which is as such. It is defined by two parameters, mu and lambda. And note that it's more complex than the Gaussian distribution. So we use the same process as usual. First of all, we take logs, and we always use the natural log here. So log of f of x is equal to a half log lambda minus a half log of 2 pi x cubed minus lambda, and then we'll expand out this square term, so x squared minus 2 mu x plus mu squared, and remember all these will be multiplied by minus lambda over 2 mu squared x. We'll simplify a bit. So we'll have the log of f of x is equal to a half log lambda minus a half log 2 pi x cubed. We'll break this down and simplify. So we have minus lambda x over 2 mu squared, and we have minus 2 mu on top and minus 2 mu squared on the bottom. Here we have x on top and x on bottom, so we will have minus times minus is a plus, lambda over mu, and then we have minus times a plus is a minus, lambda, we've mu squared on top and mu squared on bottom, they will cancel out to x. And then we can think about exponentiating. So next bit is exponentiate. So we get f of x is the exponential of all of this, and we'll start by bringing things over into the form that we are familiar with. So we have lambda minus lambda over 2 mu squared times x plus lambda over mu minus lambda over 2x, and then plus a half log of lambda minus a half log of 2 pi x cubed. Then we compare to the desired form, which is f of x is equal to the exponential of theta x minus b of theta over a of phi plus c of x and phi. So the first thing we think about here when we're looking at this is this term here, which is linked with x, has a lambda and a mu squared in it. But we also see that x is linked to lambda here, but it's a denominator. This we would not like to try to deal with, so we'll think about as theta as being a function of mu squared as opposed to being a function of lambda. Sometimes thinking ahead about what you're looking at, we're going to say theta x over a of phi is equal to minus lambda over 2 mu squared x. And if we let theta equal 1 over mu squared, we have 1 over a of phi is equal to minus lambda over 2. So a of phi is equal to minus 2 over lambda. And we'll then, for simplicity, we'll let phi equal 1 over lambda. So a of phi is equal to minus 2 phi. In making this decision, we now have to deal with this mu here. So if we say theta equals 1 over mu squared, we would say theta to the half is equal to 1 over mu. That's dealt with this 1 over mu here, and we don't see mu anywhere else. So we would rewrite this equation here in terms of theta and phi. So the first bit we have is f of x is equal to the exponential of theta x over minus 2 phi. Then we have lambda over mu. Well, we have phi is equal to 1 over lambda. So 1 over phi is equal to lambda. So we plus 1 over phi, that's the lambda taken care of. 1 over mu is theta to the half, so we've theta to the half. And then we have minus phi. So this is minus 1 over phi. And times 2x. Minus a half log of phi, because I would have had 1 over phi here. And minus a half log 2 pi x cubed. All that remains to be done is put this over 2 phi so that I have a common term here. So I have theta x minus 2 theta to the half over minus 2 phi. I've just multiplied this above and below the line by minus 2. Minus 1 over 2 phi x, and then minus a half, and I'm grouping these two terms together for simplicity, log of 2 pi phi x cubed. All of this becomes my c of x, in terms c of x and phi. B of theta is equal to minus, so it's equal to, well, you've got the minus here, so it's equal to 2 theta to the half, and we've already identified a of phi as being minus 2 phi. At this point, we can now find the mean and variance quite simply. So we get the expected value. So the expected value of x is d theta of b of theta, which is twice d theta of theta to the half, which is theta to the minus a half, because you bring your half down and these cancel out. So it's 1 over theta to the half, which is mu, as expected. The variance of x is a of phi d squared d theta to b squared, b of theta, which is equal to your a of phi, which is minus 2 phi, times d theta of theta to the minus a half, and if we think about this quite carefully, we will see that everything cancels out quite nicely. You get to the minus a half over that times a half, so we get the minus times the minus cancels out, the half cancels out with the 2, so we get phi times theta to the minus 3 over 2. We recall theta to the minus a half is equal to mu, so theta to the minus 3 over 2 is equal to mu cubed, and phi is equal to 1 over lambda, so the variance of x, which is equal to phi times theta to minus 3 over 2 equals mu cubed over lambda. So both our mean and variance match up with our expected answers, which is always comforting. It remains then to think about what function takes your expected value of x So what function g takes your expected value of x to theta? So what function takes g of theta to the minus a half to theta? And this is your canonical link function.